In the realm of aviation, where speed reigns supreme, join us on a journey through history as we explore the pursuit of the highest Mach numbers ever achieved by aircraft. The North American X-15 was a marvel of the skies, bold, sleek, and faster than any other manned aircraft in history. Despite its maiden flight over 6 decades ago, it still holds the title of the swiftest manned aircraft ever to grace the heavens. Resembling a bullet more than a conventional plane, this rocket-powered marvel completed an impressive 199 test flights spanning 9 years, commencing in 1959. Its capabilities extended to reaching the fringes of space before gradually gliding back to Earth, gathering invaluable data that would shape the future design of American spacecraft, including NASA's iconic space shuttles. A select group of only 12 elite pilots, among them the legendary Neil Armstrong, had the privilege of piloting this extraordinary craft, paving the way for historic achievements like the 1969 moon landing. Christian Geltzer, chief historian at NASA's Armstrong Flight Research Center, once described the X-15 as the pinnacle of aviation aspiration, a thrilling blend of speed, excitement, and apprehension that no other aircraft has matched since. The X-series, encompassing over 60 experimental aircraft developed by various US government agencies post-World War II, was a testament to the nation's relentless pursuit of aerospace innovation. These groundbreaking machines, epitomized by the X-15, consistently pushed the boundaries of what was considered possible. When the X-15 project took flight in 1952, it set its sights on a lofty goal, shattering the existing airspeed record, which at the time hovered just below 700 miles per hour. The primary objective of the X-15 was to achieve the remarkable feat of reaching Mach 5, equivalent to 5 times the speed of sound, or nearly 4,000 miles per hour. This endeavour posed immense challenges, remarked Geltzer. Not only did the aircraft have to attain such staggering speeds, but also had to soar to an altitude of 250,000 feet, surpassing any previous aircraft's operational ceiling. It was an exceedingly ambitious goal. Led by the US Air Force and the precursor to NASA, the National Advisory Committee for Aeronautics, NACA, the project aimed not only to gather scientific and flight dynamics data, but also operated against the backdrop of the Cold War, driving a sense of urgency and motivation behind the research efforts. Unlike conventional aircraft, the X-15 resembled more of a rocket with a cockpit, necessitating a unique launch procedure. Instead of taking off from a runway, it relied on being carried aloft by a mothership, specifically a specially modified B-52 bomber. With the X-15 nestled beneath its wing, the B-52 would depart from Edwards Air Force Base in Southern California, embarking on a trajectory towards Nevada or Utah. Upon reaching the designated release point, typically at an altitude exceeding 45,000 feet and a speed surpassing 600 miles per hour, the X-15 will be set free to commence its ascent into the heavens. Only then would the X-15 pilot ignite the rocket engine, propelling the aircraft out of Earth's atmosphere and into the realm of space. The propulsion system, comprising a blend of ammonia and liquid oxygen, provided a mere 2 minutes of thrust, subjecting the pilot to a tumultuous and challenging journey. It flew aerodynamically like a normal airplane, but it climbed like nobody's business, said Geltzer. Milt Thompson, who was one of the pilots, said that it was the only airplane he ever flew in which he was glad when the engine quit. Once the X-15 reached its target altitude, which soared as high as 354,200 feet, approximately 10 times the cruising altitude of a typical commercial airliner, the pilots embarked on a series of groundbreaking experiments in this uncharted realm, contributing invaluable data to our understanding of hypersonic flight. Much of the X-15's engineering was tailored to accommodate high-altitude operations, where the atmosphere becomes so tenuous that traditional aerodynamic control surfaces become ineffective. To address this challenge, the X-15 was outfitted with a pioneering reaction control system reminiscent of those later employed by space shuttles and the International Space Station. This system expelled bursts of hydrogen peroxide, a highly concentrated oxygenated form of water, generating modest thrust, capable of maneuvering the aircraft within the rarefied upper atmosphere. Travelling at velocities reaching thousands of miles per hour, the outer surface of the X-15 endured intense heating caused by aerodynamic friction. To withstand these extreme conditions, the aircraft's skin was crafted from a specialized nickel-chromium alloy known as Inconel-X. The aircraft heated up to 1,200 degrees Fahrenheit, Geltzer said, and the pilots could hear it expand behind them. Landing the X-15 wasn't easy. From the moment it ran out of fuel or the pilot turned off the engine, it was a glider. A very heavy, very fast glider with very small wings, so not even a great glider. At that point, the pilot only had speed and altitude to exchange for reaching his destination, said Geltzer. Adding to the challenges, the X-15 faced limitations in its landing gear configuration. With a front wheel lacking steering capabilities and main landing gear featuring only skids, retractable steel beams that slid along the landing surface, a traditional tarmac runway was out of the question. Consequently, the aircraft was compelled to land on a dry lake bed. After each flight, the aircraft returned to base transformed, bearing witness to the punishing conditions it endured. The heat had left its mark, with visible burns and holes, Geltzer noted. While conventional aircraft typically execute final landing approaches at speeds below 200 miles an hour, the X-15 operated under vastly different circumstances. It commenced its descent from altitudes of up to 20,000 feet, hurtling towards the ground at supersonic speeds exceeding 1,500 miles per hour, an experience far removed from the norm for most pilots. Regrettably, not every flight concluded without incident. This was an experimental aircraft, and things went wrong almost every single slide. The remarkable feat is that the pilots consistently managed to bring the aircraft back despite the challenges, Geltzer remarked. Of the nearly 200 flights undertaken, only 2 ended in crash landings, tragically resulting in the loss of pilot Michael Adams. On November 15, 1967, Adams encountered a spin during re-entry, unable to stabilize the aircraft, which ultimately disintegrated in mid-air. The inherent dangers associated with piloting this hybrid aircraft, part plane and part spaceship, partly explain why the X-15's records remain unchallenged by modern engineering. Moreover, it served as a crucial precursor to the space program, which aspired to achievements beyond mere speed. Yet the X-15's legacy endures as one of the most triumphant flight research programs in history. Over its 9-year tenure, it amassed invaluable data on high-speed flight, space re-entry, and human physiology. In 1967, pilot Pete Knight set a record speed of 4,520 miles per hour, equivalent to Mach 6.7. During one of his 7 X-15 flights, Armstrong demonstrated the problem-solving acumen that would later propel him to command Apollo 11. In 1962, he embarked on a flight reaching 205,000 feet, a Mach 3.8, Geltzer recounted. On the return journey, he encountered an unprecedented bounce off the upper atmosphere at around 90,000 feet, akin to skipping a stone. Despite losing power and finding himself over a Los Angeles suburb, Armstrong skillfully guided the aircraft back, executing a successful landing on Rogers Dry Lake. It remains the longest X-15 flight on record. NASA achieved a significant milestone in aviation by successfully conducting the first and second flights of a scramjet-powered aircraft at hypersonic speeds, exceeding Mach 5 or 5 times the speed of sound.
Unlike conventional rockets that must carry its own oxygen to operate, scramjets are air breathers that obtain oxygen from the air in which it's flying, and this characteristic allows for much more airplane-like operations with increased safety, affordability, and flexibility.
The NASA Hyper-X program, spanning 8 years with an investment of around $230 million, represented a bold initiative in research, pushing the boundaries of what had been previously attempted. The successful March 2004 flight marked the first instance of an air-breathing engine-powered vehicle achieving hypersonic velocities. The intricate process of rocket propulsion, followed by scramjet operation, presented a series of technical challenges, all of which needed to be meticulously addressed for mission success. Despite thorough analyses and design optimizations aimed at mitigating risks, some residual risk remained inherent to the program. The Hyper-X research initiative began in 1996 with conceptual development and experimentation in wind tunnel environments. 3 unpiloted X-43A research aircraft were built. Each of the lifting body vehicles, measuring 12 feet in length and 5 feet in width, was designed for a single flight without recovery. While visually identical, these vehicles were engineered with subtle variations to simulate different engine configurations, typically corresponding to various Mach numbers. The initial 2 vehicles were optimized for flight at Mach 7, while the third was tailored for Mach 10 velocities. Operating at such velocities, the four-body shape of the vehicle functioned akin to pistons in an engine, compressing air as fuel was injected for combustion. The X-43A utilized gaseous hydrogen as its fuel source.
The ultimate goal of hypersonics really is twofold. One is to reduce the cost for access to space. Routinely getting to space with this type of technology or using this technology, an operational space access vehicle is a goal. The second goal, and probably one that's farther out, granted, but maybe 100 years out, but hypersonic commercial travel, I think, can be a reality someday and anywhere in the globe in just a few hours.
Following an unsuccessful launch attempt in June 2001 due to booster rocket malfunction, subsequent flights in March and November 2004 achieved remarkable success, breaking speed records. In March 2004, the X-43A attained a velocity of Mach 6.8, shattering the previous record for air-breathing vehicles. During its final flight at nearly Mach 10, the X-43A reached a speed of 6,755 miles an hour at an altitude of 110,000 feet, establishing a new world speed record for air-breathing vehicles. The Mach 10 vehicle was equipped with enhanced thermal protection, including the integration of carbon-carbon composite material on the leading edges of its vertical fins to withstand higher temperatures. Both flights commenced with the B-52B aircraft transporting the stack to a predetermined location over the Pacific Ocean, 50 miles west of the Southern California coast. The release altitude from the B-52B was consistent at 40,000 feet for both successful flights, from which point the booster propelled each research vehicle to its designated test altitude and velocity. Aside from variations in altitude, speed and distance covered, the flight profile of the Mach 10 mission mirrored that of the Mach 7 flight. Following separation from the booster, the Mach 10 research vehicle autonomously flew according to pre-programmed commands. Separation from the booster was facilitated by 2 small pistons. Shortly thereafter, the Scramjet engine operated for approximately 10 seconds, yielding substantial and unique flight data for an integrated Scramjet system. Throughout both flights, the engine's thrust closely matched its design specifications, enabling acceleration during the Mach 7 flight and sustained cruising at constant velocity during the Mach 10 flight. Upon completion of the Scramjet engine test, each vehicle transitioned into a high-speed maneuvering glide, gathering nearly 10 minutes of hypersonic aerodynamic data en route to a designated mission completion point. For the Mach 7 flight, this point was located approximately 450 miles west, while for the Mach 10 flight, it extended to 850 miles west, within the Naval Air Warfare Center Weapons Division sea range off the southern coast of California. As planned, both vehicles descended into the ocean upon completion of their missions without any recovery efforts undertaken. The achievements of reaching Mach 6.8 and Mach 9.6 have been officially recognized by Guinness World Records, appearing on their website in the 2006 edition of their record book. The inaugural flight attempt of the X-43A took place in June 2001. However, it was unsuccessful due to booster failure, leading to its premature termination. Consequently, the research vehicle didn't undergo testing as it did not reach the required test conditions. Although no single contributing factor was found, the root cause of the problem was identified as the booster's flight control system. The booster's failure stemmed from inaccuracies in design models, which had overestimated the flight control system's capability to function within anticipated flight conditions. The Hyper-X program has played a pivotal role in pushing the boundaries of air-breathing flight, notably achieving the milestone of flying a scramjet-powered aircraft at hypersonic speeds for the first time. Various measures were implemented in response to the identified issues. These included conducting wind tunnel tests to gather data aimed at reducing atmospheric loads on the booster's control surfaces, enhancing booster fin actuators to better withstand aerodynamic forces, and adjusting propellant levels in the Pegasus booster to facilitate launches at the standard altitude of 40,000 feet, as opposed to the lower altitude of 23,000 feet utilized during the initial flight. A ramjet engine functions by combusting fuel in a stream of air compressed by the aircraft's forward speed, in contrast to conventional jet engines, where the compressor section compresses the air. Ramjets typically operate within the Mach 3 to Mach 6 range. Scramjets represent an advancement of ramjet technology, maintaining supersonic airflow through the engine. Envisaged applications for scramjet-powered vehicles extend to speeds exceeding Mach 15. While ground tests of scramjet combustors have demonstrated this potential, flight tests have yet to surpass the achievement of the Mach 9.6 flight attained by the X-43A. The Hyper-X program, managed by the Aeronautics Research Mission Directorate in Washington, was conducted jointly by the Langley Research Center in Hampton, Virginia, and the Dryden, now Armstrong, Flight Research Center in Edwards, California. Langley served as the lead center, spearheading the development of hypersonic technology. Dryden's responsibilities encompassed flight research, hardware integration, and testing. NASA's Aeronautics Research Mission Directorate is dedicated to advancing tools and technologies that can revolutionize air transportation operations, aircraft design, and manufacturing processes, and enhance the safety of the nation's air transportation system. The Lockheed YF-12 represented a pinnacle of American aerospace engineering, boasting Mach 3+ capability and high-altitude interception potential. Developed and produced by Lockheed Corporation, this Interceptor emerged during the late 1950s and early 1960s as a candidate to replace the F-106 Delta Dart Interceptor within the United States Air Force. President Lyndon B. Johnson publicly disclosed the existence of the YF-12 on February 24, 1964, primarily to provide a cover story for the CIA-operated A-12 fleet, which closely resembled the newly revealed prototype. Despite undergoing rigorous flight evaluations by the USAF during the 1960s, operational deployment of the YF-12 was thwarted by funding constraints, compounded by the difficulties of the Vietnam War and other military imperatives. Nevertheless, it secured and maintained speed and altitude records exceeding 2,000 miles per hour, 3,200 kilometers an hour, and soaring beyond 80,000 feet, 24,000 meters, subsequently eclipsed by its successor, the SR-71 Blackbird. Remarkably, the YF-12 holds the distinction of being the world's largest, heaviest, and fastest crewed interceptor. After its retirement from USAF service, the YF-12 found new life as a research platform for NASA, contributing to advancements in supersonic aircraft control systems. Originating from the Long Range Interceptor Experimental LRIX initiative, which initially considered the North American XF-108 Rapier, the YF-12's genesis, intertwined with Lockheed's A-12 reconnaissance program, was overseen by the CIA under the Oxcart program. Under the visionary leadership of Kelly Johnson at Lockheed Skunk Works, the YF-12 emerged as a derivative of the A-12, designated as the AF-12, and subsequently configured as the YF-12A Interceptor. The transformation of the A-12 reconnaissance aircraft into the YF-12A Interceptor involved several key modifications, chiefly centered around accommodating the formidable Hughes AN/ASG-18 fire control radar originally intended for the XF-108 Interceptor. The A-12's nose underwent alterations, including the reduction of the chines to integrate the large radar, along with embedding two infrared search and track sensors into the chine leading edge. Additionally, a second cockpit was installed to house a crew member responsible for operating the fire control radar for the air-to-air missile system. These modifications significantly altered the aircraft's aerodynamics, necessitating the addition of ventral fins under the fuselage and engine nacelles to maintain stability. Moreover, 3 of the A-12's 4 bays were repurposed to accommodate Hughes AIM-47 Falcon GAR-9 missiles, while 1 bay was dedicated to fire control equipment. The YF-12A's maiden flight took place on August 7, 1963, although its existence was not publicly acknowledged until President Lyndon B. Johnson's announcement on February 24, 1964. This revelation served to divert attention from the still classified A-12 program. The YF-12A was showcased to the public for the first time on September 30, 1964 at Edwards Air Force Base. Despite the promising performance of the YF-12A and the subsequent order of 93 F-12B aircraft for the Air Defense Command, the program faced setbacks due to funding constraints driven by the escalating costs of the Vietnam War. Secretary of Defense Robert McNamara withheld funding for 3 consecutive years, leading to the cancellation of the F-12B program in January 1968. During flight tests, the YF-12A set impressive speed and altitude records, reaching 2,070.101 miles per hour, 3,331.505 kilometers an hour, and 80,257.86 feet, 24,462.6 meters, respectively, on May 1, 1965. The unique weapon system of the YF-12A also demonstrated promise, with 6 successful firings of the AIM-47 missiles completed. Although 1 missile failed due to gyro malfunction, the remaining missiles showcased their effectiveness, including a remarkable hit on a JQB-47E target drone at Mach 3.2 and an altitude of 74,000 feet, 23,000 meters, resulting in a direct hit and significant damage. The YF-12 program faced significant challenges despite its successes, particularly in securing further funding and addressing control issues that affected both engine performance and physical aircraft control. Secretary of Defense McNamara redirected funding from the YF-12 program to the F-106X program, which faced difficulties and was less successful. Despite this setback, developments from the YF-12 program found applications in subsequent projects. The AIM-47 Falcon missile, proven successful during YF-12 testing, underwent enhancements to become the AIM-54 Phoenix missile used on the F-14 Tomcat. Additionally, upgrades to the AN/ASG-18 radar resulted in the AN/AWG-9 and APG-71 systems, which provided improved tracking capabilities for multiple targets. Jim Irwin, one of the Air Force test pilots involved in the YF-12 program, transitioned to become a NASA astronaut and famously walked on the moon. Although the production of the F-12B was cancelled, the YF-12 aircraft continued to serve both the USAF and NASA as research aircraft for many years. NASA conducted tests to address various engineering challenges, including engine inlet performance, boundary layer noise, heat transfer under high Mach conditions, and altitude hold at supersonic speeds. These tests were crucial for advancing the understanding of supersonic flight. The YF-12 and the SR-71 initially faced control issues, but wind tunnel testing and research flights led to the development of computer systems that significantly improved performance and stability. The implementation of systems like the Central Airborne Performance Analyzer and the Cooperative Airframe Propulsion Control System played crucial roles in enhancing the control of supersonic aircraft during flight, addressing issues such as engine unstarts and improving overall stability and performance. The challenges of controlling aircraft at such high speeds were significant, with even minor changes in direction leading to substantial deviations in position, often accompanied by severe temperature and pressure changes. The implementation of the Cooperative Airframe Propulsion Control System played a crucial role in mitigating these deviations, reducing them by a factor of 10. These improvements not only enhanced the stability and control of the aircraft, but also increased the range of the SR-71 by 7%, demonstrating the effectiveness of the system in optimizing performance. Unfortunately, the YF-12A program experienced losses during its operational lifespan. One of the aircraft, designated AF serial number 606934, was damaged beyond repair in a landing mishap at Edwards Air Force Base on the 14th of August 1966. Another YF-12A, AF serial number 606936, was lost on the 24th of June 1971 due to an in-flight fire caused by a failed fuel line. Fortunately, both pilots ejected safely, averting a potential disaster. The sole surviving YF-12A, designated AF serial number 606935, was recalled from storage in 1969 for a joint investigation by the USAF and NASA into supersonic cruise technology. It was subsequently transferred to the National Museum of the United States Air Force at Wright-Patterson Air Force Base near Dayton, Ohio, where it remains as a testament to the pioneering era of high-speed, high-altitude flight research. The experimental X-51A WaveRider serves as an unmanned autonomous hypersonic flight test demonstrator powered by a supersonic combustion ramjet Scramjet engine commissioned by the US Air Force. Launched from an airborne B-52 Stratofortress bomber, the X-51A comprises a stack approximately 25 feet in length, incorporating a modified solid rocket booster sourced from an Army tactical missile, an interstage connection, and the X-51A cruiser itself. The cruiser, nearly devoid of wings, derives its moniker WaveRider from its unique design feature of riding its own shockwave. This distinctive aircraft boasts small, controllable fins and houses the core component, a Pratt & Whitney Rocketdyne SJY-61 Scramjet engine engineered to burn JP-7 jet fuel. Boeing's Phantom Works spearheaded the overall air vehicle design, assembly and testing, employing standard aerospace materials such as aluminum, steel, Inconel and titanium, supplemented by carbon-carbon composites for leading edges of fins and cowls. To withstand the intense thermal conditions, the X-51A integrates a silica-based thermal protection system developed by Boeing alongside reusable insulation tiles akin to those utilized on NASA Space Shuttle orbiters. The Air Force commissioned the construction of 4 X-51As, emphasizing the program's role as a technology demonstrator rather than as a prototype for a specific weapon system. Its primary objective is to advance hypersonic weaponry, intelligence, surveillance, reconnaissance capabilities, and enhance future access to space. The ability of scramjets to utilize atmospheric oxygen negates the need for large onboard oxidizer tanks, typical of conventional rockets, promising more efficient payload launches into orbit. Alongside scalable scramjet propulsion, the X-51A will showcase advancements in thermal protection systems materials, airframe and engine integration, and high-speed stability and control. Representing a significant reinvestment in hypersonic flight, the X-51A program stands as a pivotal milestone for the Air Force, echoing the pioneering spirit of the rocket-powered X-15 program that preceded it by half a century. Air Force officials foresee the X-51A program as a pivotal platform for acquiring the essential knowledge needed to propel future advancements in space access and hypersonic weaponry. The program's potential for hypersonic speeds, such as covering 600 nautical miles in just 10 minutes, promises rapid and precise engagement of distant targets, a capability with transformative implications. a collaborative endeavour between the Air Force Research Laboratory, the Defence Advanced Research Projects Agency, DARPA, and industry partners, the Boeing Company and Pratt & Whitney Rocketdyne, the X-51A program is managed by the Air Force Research Laboratory Propulsion Directorate at Wright-Patterson Air Force Base, Ohio. Hypersonic flight, commencing at Mach 5, presents distinctive technical hurdles involving extreme heat and pressure, rendering traditional turbine engines impractical. Generating thrust with a scramjet engine is likened to maintaining a flame in a hurricane, an analogy underscoring the formidable challenges faced by program officials. The Air Force intends to execute identical flight profiles for each X-51A, akin to the operational approach of the X-15. Following this same deployment method as its predecessor, the X-51A is hoisted aloft by a B-52 mothership from the Air Force Flight Test Center at Edwards Air Force Base, California. Upon reaching approximately 50,000 feet above the Pacific Ocean's Point Mugu Naval Air Warfare Center sea range, the solid rocket booster propels the X-51A to around Mach 4.5 for 30 seconds before detaching. Subsequently, the cruiser's scramjet engine initiates, distinguished by its minimal moving parts, initially burning ethylene and transitioning over a span of roughly 10 seconds to the JP-7 jet fuel previously employed by the SR-71 Blackbird. Powered by its scramjet engine, the X-51A accelerates to approximately Mach 6 while ascending to nearly 70,000 feet. Hypersonic combustion generates intense heat, so routing the engine's own JP-7 fuel will serve to both cool the engine and heat the fuel to optimum operating temperature for combustion. The X-51A's fuel load and flight profile facilitate a 240-second engine burn, during which extensive telemetry data on its systems is transmitted to orbiting aircraft and ground stations. As planned, the vehicle exhausts its fuel supply, ultimately splashing down into the Pacific Ocean, where it meets its preordained demise. Flight test vehicles are intentionally not recovered, a decision made by the X-51A development team from the outset to streamline costs and prioritize funding toward perfecting the vehicle's fuel-cooled scramjet engine. During flight, telemetry data is relayed to engineers stationed at Naval Air Station Point Mugu and Vandenberg Air Force Base, California, via a U.S. Navy P-3 Orion aircraft. This information is then forwarded to the Ridley Mission Control Center at Edwards Air Force Base, where it undergoes analysis. Conceived in 2004, the X-51A embarked on its inaugural captive carry flight on December 9, 2009, validating the B-52's performance and handling characteristics at high altitudes with the X-51 attached. Communication and telemetry systems were also tested during this flight, albeit with the vehicle remaining attached to the B-52's wing. The X-51A etched its name in the annals of aviation history during its maiden supersonic combustion ramjet-powered hypersonic flight on May 26, 2010, off the coast of Southern California. Demonstrating flawless performance, the scramjet propelled the vehicle to approximately Mach 5, or nearly 3,400 miles per hour, for nearly 200 seconds. Although telemetry remained normal for over 140 seconds, a decrease in thrust and acceleration occurred during the subsequent 30 seconds, followed by an anomaly resulting in a loss of telemetry. Consequently, flight controllers terminated the test and commanded the destruction of the vehicle. Despite the anomaly, the May 26 flight marked the inaugural use of a practical hydrocarbon-fueled scramjet in flight. Notably, this achievement surpassed the longest previous hypersonic scramjet flight test conducted by a NASA X-43 in 2004, which, although faster, lasted only about 12 seconds and employed less logistically supportable hydrogen fuel. Subsequent to an exhaustive analysis of flight data from the X-51A's maiden hypersonic flight, slight modifications are slated to reinforce the rear seal area near the engine exhaust nozzles for the 3 remaining X-51As. Regrettably, the following 2 X-51A flights concluded prematurely. During the second X-51A flight, the vehicle was propelled by the rocket to slightly above Mach 5 before disengaging and activating the scramjet engine fueled by ethylene. However, upon attempting to transition to JP-7 fuel operation, an inlet unstart occurred. Despite efforts to restart and optimize engine start conditions, the vehicle remained unsuccessful in its attempts. It maintained controlled flight orientation until ultimately descending into the ocean within the test range. In the case of the third X-51A, a successful separation from the B-52 was followed by 16 seconds under the rocket booster, after which a fault was detected with one of the cruiser's control fins. Subsequently, upon detachment from the rocket booster roughly 15 seconds later, the cruiser lost control due to the malfunctioning fin and was ultimately lost. Conversely, the final flight of the X-51A on May 1, 2013 proved to be the most successful, achieving all experiment objectives. The cruiser traversed more than 230 nautical miles in just over 6 minutes, attaining a peak speed of Mach 5.1. In totality, the X-51A program amassed over 9 minutes of invaluable data, marking a groundbreaking accomplishment and validating the feasibility of air-breathing, high-speed scramjet propulsion utilizing hydrocarbon fuel. On May 1, 1960, amidst the escalating tensions of the Cold War, Gary Powers found himself in a harrowing situation. His U-2 aircraft, employed for reconnaissance missions, was struck by Soviet surface-to-air missiles, plummeting from 70,000 feet to 30,000 feet before Powers managed to release himself and bail out from the damaged cockpit. Meanwhile, at Lockheed's Skunk Works in Burbank, California, a team of engineers had already embarked on a groundbreaking project, the development of an aircraft that would revolutionize intelligence gathering. This aircraft, envisioned to fly faster and at greater altitudes than any before it, with minimal radar cross-section, was deemed essential in the tense geopolitical climate of the time. President Eisenhower recognized the strategic importance of airborne reconnaissance, particularly in light of the U-2's contributions. In response to the urgent need for an aircraft resistant to enemy fire, Lockheed received a directive from its government client in Washington to create the seemingly impossible, a plane impervious to interception. Led by the renowned aircraft designer Kelly Johnson, the Skunk Works team was renowned for its ability to deliver groundbreaking technologies under tight deadlines. The U-2 project was a testament to their resourcefulness, creativity, and unwavering determination in the face of technological challenges. The task at hand was unprecedented. Johnson acknowledged that every aspect of the aircraft had to be innovated from scratch. Undeterred by the daunting nature of the endeavour, he committed Skunk Works to achieve the seemingly unsurmountable goal of having the revolutionary aircraft operational within a mere 20 months. The envisioned aircraft was unlike anything seen before. It was designed to sustain speeds exceeding 2,000 miles per hour for extended durations, a feat unparalleled in aviation history. Conventional airframes would succumb to the extreme temperatures generated by friction with the atmosphere at such velocities, necessitating radical innovations in design and materials. The challenges posed by the extreme temperatures anticipated on the aircraft's leading edges, exceeding 1,000 degrees Fahrenheit, presented formidable hurdles in design and material selection. Titanium alloy emerged as the sole viable option for the airframe, offering the strength of stainless steel, lightweight properties, and resilience to the intense heat. However, working with titanium proved to be a complex endeavour. The brittle nature of the alloy demanded meticulous handling, leading to frustrations on the Skunk Works assembly line and necessitating specialized training for Lockheed's machinists. Conventional tools, plated with cadmium-plated steel, proved detrimental to titanium, prompting the development and fabrication of new tools crafted from titanium itself. While the leading edges of the aircraft faced scorching temperatures, the exterior environment outside the cockpit window could plummet to -60 degrees Fahrenheit. Addressing the challenge of heat dissipation across the entire airframe, Ben Rich of Skunk Works drew inspiration from a basic lesson learned in university. Black paint possesses both heat-emitting and heat-absorbing properties. Consequently, the aircraft was coated in black paint, earning it the moniker Blackbird. The inaugural iteration of the Blackbird, designated the A-12, embarked on its maiden flight on April 30, 1962. Subsequently, the single-seat A-12 evolved into the larger SR-71, featuring an additional seat for a reconnaissance systems officer and increased fuel capacity. The SR-71 conducted its maiden flight on December 22, 1964. Efforts to diminish the Blackbird's radar signature aimed to further minimize the likelihood of detection and interception. Despite promising initial test outcomes, concerns over Soviet radar advancements prompted the US government to demand an even smaller radar profile, underscoring the ongoing quest for technological superiority in the realm of aerial reconnaissance. Redesigning surfaces to minimize radar reflection, relocating engines to a more inconspicuous mid-wing position, and incorporating radar-absorbing elements into the paint were among the meticulous adjustments made to the Blackbird's design. Subsequently, a full-scale model of the aircraft underwent radar testing at a clandestine location in the Nevada desert, meticulously scheduled to evade detection by Soviet satellites. The outcomes were striking. The Blackbird model, spanning over 100 feet, appeared on Soviet radar as larger than a bird, yet smaller than a man, effectively reducing its radar cross-section by an impressive 90%. The urgency to deploy the Blackbird heightened on October 27, 1962, amidst the Cuban Missile Crisis, following the tragic death of Air Force Major Rudolph Anderson during a U-2 reconnaissance mission over Cuba, struck by a Soviet surface-to-air missile. Skunk Works redoubled its efforts, confronting and surmounting the myriad challenges encountered during flight testing as it pushed the boundaries of aeronautical achievement. Breaking records with nearly every flight, the Blackbird reached a sustained speed surpassing Mach 3 on July 20, 1963, soaring to an astonishing altitude of 78,000 feet. As the aircraft traversed the skies at 3,000 feet per second, conventional navigation norms became obsolete, replaced by landmarks such as mountain ranges, coastlines, and expansive bodies of water. Piloting the Blackbird demanded unwavering focus and skill, with pilots facing the formidable task of navigating at incredible speeds and altitudes. Despite the formidable challenges, the exhilarating responsibilities of flying the Blackbird left pilots awestruck and exhilarated. Air Force Colonel Jim Watkins reflected on the experience, describing it as almost transcendent, with memories of soaring at 85,000 feet and Mach 3 evoking profound emotions even years later. At such unparalleled speeds and altitudes, even the most advanced air defense systems stood little chance of intercepting the Blackbird. When enemy aircraft weapons were launched, a warning light illuminated on the control panel, signaling imminent danger. However, for the pilot, this often marked the extent of the threat, as surface-to-air missiles consistently veered off course, detonating miles away from their intended target. The Blackbird's legacy is adorned with numerous records. It holds the distinction of being the world's fastest and highest-flying manned aircraft. During its retirement journey from Los Angeles to Washington in 1990, en route to its final resting place in the Smithsonian Air and Space Collection, the aircraft traversed the entire continental United States in a mere 67 minutes. Above all, the Blackbird fulfilled its strategic imperatives, providing invaluable mission-critical reconnaissance for over 2 decades. The extent of its intelligence-gathering contributions during the Cold War remains largely known only to a select few. Nevertheless, its reputation as a transformative force will endure for generations to come, symbolizing innovation, resilience, and technological prowess in the annals of aviation history.
The X-15, designed to be purely and simply a research vehicle to provide aerodynamic, flight dynamic, and structural response data for use in the development of future manned hypersonic vehicles such as the Space Shuttle. No hypersonic wind tunnels, past or present, can provide accurate data for the design of a full-scale hypersonic airplane. The frontiers of flight today are the same as they were in the 1950s, the exploration of hypersonic flight. The X-15 will ultimately be viewed as the Wright Flyer of hypersonic airplanes. The X-15 flew to speeds and altitudes never previously achieved by winged vehicles. On the crisp, clear morning of November 9, 1961, A prospector working any of the many small mining claims in the bleak country around Mud Lake would have noticed the telltale broad white contrail signaling the approach of a strange formation of aircraft. If his eyesight was particularly acute, he might have discerned a giant Boeing B-52 Stratofortress arrowing through Nevada's dark blue sky, flanked by two sleek little fighters, a North American F-100 Super Sabre and a Lockheed F-104 Starfighter. As he watched, he might have seen a long black dart drop from the B-52, followed by the sudden boom and crackling rumble of an igniting rocket engine. Boosted by 60,000 pounds of thrust, it leapt ahead of the big bomber and its chase planes, accelerating upwards as it burned a ton of anhydrous ammonia and liquid oxygen every 12 seconds. It arced into the trans-atmosphere, its white exhaust trail pointing like a finger toward the future. Not quite 90 seconds later, it was level at 102,000 feet, streaking towards Edwards Air Force Base in Southern California at Mach 6.04. Air Force test pilot Major Robert White had just become the first man to take an airplane to Mach 6, 6 times the speed of sound, flying the second of 3 North American Aviation X-15 research airplanes. Slightly less than 8 minutes and 200 miles later, trailed by another F-104 chase plane, the X-15, its propellants exhausted and now the world's fastest glider, dropped into a steep curve to a landing flare and touchdown on runway 18, marked out on the hard-baked clay of Rogers Dry Lake, the world's largest natural landing site. The X-15 program was a natural outgrowth of progression of aviation since the time of the Wrights. The biplane had given way to the streamlined monoplane, and by the late 1930s, the first experimental jet engines had appeared, promising an era of high-speed flight. But as an airplane flew closer to the speed of sound, it encountered compressibility, the bunching up of air around it as it neared Mach 1, causing high drag, buffeting, changes in structural loads, and even loss of control and in-flight breakups. For more than a decade, until Chuck Yeager flew the first Bell XS-1, later X-1, to Mach 1.06 in October of 1947, it seemed that the speed of sound might indeed be a barrier to the future flight. Afterward, aviation accelerated rapidly into the supersonic era. Mach 2 fell to Scott Crossfield, and the second Douglas D-558-2 skyrocket in November 1953, and Mach 3 to Captain Milburn Apt and the first Bell X-2 in September 1956, though tragically, he perished when the plane went out of control during its return to Edwards. By the time of Apt's death, the X-15 program was well underway. Its designers faced formidable challenges. Bell had built advanced variants of the X-1 that could excel at Mach 2 and 90,000 feet, and the swept-wing X-2 could climb above 125,000 feet. Both hinted at control challenges the X-15 would face. In 1956, when test pilot Captain Ivan C. Kinch coasted to above 126,000 feet, his X-2 was like an artillery shell following a ballistic parabola. Near the top of its climb, as the plane decelerated after its rocket engine ran out of propellant, its ailerons, elevators, and rudder were useless due to the very low dynamic pressure encountered as it passed through the upper atmosphere. The X-2 began a slow left roll, arced over the top of its ballistic parabola, and, as its speed and, consequently, dynamic pressure increased in the lower atmosphere, its flight controls regained their effectiveness, and Kinchlow was able to guide it back to a safe landing on Edwards Broad lakebed. Clearly, flying above 100,000 feet, future rocket planes would require reaction controls, small jet thrusters such as those employed on the first manned spacecraft, in addition to conventional aerodynamic control surfaces. Aerodynamic heating and the high-altitude environment pose their own problems. Unlike supersonic flight, which is differentiated by the speed of sound and the distinctive crack of a sonic boom, hypersonic flight is characterized primarily by increasing aerodynamic heating with intensity hot airflows and sharply angled shock waves washing over the structure, their interactions producing even greater heat. The structure could not be conventional. for the plane would be subject to skin temperatures above 1,000 degrees Fahrenheit, necessitating extensive thermal protection. Inside the fully pressurized cockpit, the pilot would be more astronaut than airman, wearing a pressure suit and helmet capable of functioning in space-like conditions should cabin pressure be lost. Interest in hypersonic flight predated the supersonic revolution. The three great prophets of the space age, Russia's Konstantin Tsiolkovsky, the Romanian-German Hermann Oberth, and America's Robert Goddard, all advocated hypersonic airplanes as a means of flying into space, and German rocket enthusiast Max Valier, before his death and the explosion of an experimental rocket engine, recommended developing rocket-powered either planes as intercontinental airliners. In the 1930s, Austrian engineer Eugen Sanger and the mathematician Irene Brett undertook the world's first science-based hypersonic design, their so-called Silbervogel, Silver Bird. Proposed as a space transport and later as a global strike aircraft, it became an extraordinarily influential design study. Right after World War II, Joseph Stalin, according to a Soviet military defector, even sent a team into Western Europe on a fruitless mission to kidnap authors, hoping that Soviet Sanga planes would make it easier for us to talk to the gentleman shopkeeper, Harry Truman. The combination of the Sanga-Brett study and example of a Nazi A4V2 ballistic missile greatly simulated post-war American, Soviet, and European interest in rockets, missiles, and hypersonic aircraft. While the Sanga-Brett study had been purely theoretical, the A4 program had extensively studied Mach 4 Plus wing derivatives, one of which, the A4B, flew before war's end, though it broke up during its terminal glide to Earth. The Soviet-American race to develop atomic-armed ballistic missiles fostered heating and reentry studies, evolution of the blunt body reentry shape, and high-temperature materials research. It also encouraged studies of rocket-boosted winged global-ranging hypersonic vehicles, even orbital spacecraft. In America, from all this sprang the X-15 and X-20 programs, though the latter never flew. The roots of the X-15 reflected a broad base of military, industrial, and governmental research support. In 1951, Robert Woods, Bell Aircraft Corporation's chief engineer and a member of the National Advisory Committee for Aeronautics, prestigious aeronautics committee, called for development of new research airplane with performance similar to the A4s. His continued pressure led NACA's executive committee to endorse, a year later, investigating flight conditions between Mach 4 and Mach 10. The agency formed a hypersonic study committee under Langley Aeronautical Laboratory, now NASA Langley Research Center, engineer Clinton Brown, which subsequently advocated greatly expanded ground and flight research tests using models and specialized test techniques. The committee even suggested modifying the X-2 with a strap-on booster to increase performance above Mach 4, adding reaction controls for flight safety. Program delays and eventual loss of both airplane doomed that idea. In 1953, the Air Force's Scientific Advisory Board concluded the time is ripe for a Mach 5 to 7 hypersonic vehicle, and the U.S. Navy's Office of Naval Research issued a study contract to Douglas for a Mach 7 Plus design, tentatively designated the D558-3. Air Force and Navy interest proved crucial to getting the X-15 program off the drawing board and into the air. The next year, 1954, marked the genesis of the X-15. Another NACA study team, headed by John Becker, undertook preliminary design of a Mach 6 rocket-boosted hypersonic research airplane. It had a nickel alloy Inconel structure, rocket-like four-fin tail, and off-shelf rockets from the Hermes program. Becker's study anticipated many of the X-15's features, and encouraged NACA that summer to invite the military services to join with it in developing such an aircraft. In October, they formed the NACA Air Force Navy Research Aircraft Committee, subsequently known as the X-15 Committee. A joint program directive issued on December 23rd gave technical oversight to NACA and design and construction authority to the Air Force. The Navy and Air Force would jointly fund the effort. The Air Force supervised a design competition in 1955 between Bell, Douglas, North American, and Republic. Bell's Robert Woods, who had launched the company's earlier X-1 effort, might reasonably have expected his firm to win, since it had already built and flown the X-1, X-2, and X-5. Douglas's Ed Heinemann, with his D-55-8 Skystreak and Skyrocket, plus the D-55-3 Study, might have as well. Both companies produced relatively cheap designs, each promising to deliver 3 airplanes for a total cost of $36 million. Harrison's Stormy Storms, a veteran of North American's many fighter programs, led the design team that drafted his firm's entry, at an estimated $56 million, the most expensive proposal. But both Bell and Douglas's designs were considered too technically risky, and Republic's, which was technically insufficient and also more costly than the Bell and Douglas proposals, came in last. Accordingly, despite the huge cost disparity, the Air Force notified North American on September 30th that it had won the competition. On June 11th, 1956, after final negotiations, North American received a $42.9 million contract, about $349 million today, for the 3 X-15s. 3 months later, Reaction Motors Incorporated was awarded with a $10.7 million contract for their engines. The X-15 program involved far more than simply designing a new airplane, however novel it might be. Its rocket engine, pilot protection system, environmental controls and flight control system, as well as its flight test range, posed complex challenges. The X-15's XLR-99 engine, more than 3 times as powerful as the X-2s and 8 times as powerful as the X-1s, proved particularly risky. Developed by New Jersey-based Reaction Motors, the XLR-99 was based on the earlier XLR-30, used in the Navy's Viking high-altitude rocket program. Any hopes that the Viking experience would help with its design proved illusory. Unlike the XLR-30, which burned diluted alcohol and liquid oxygen, the 57,000-pound thrust XLR-99 burned 1,445 gallons of more explosive anhydrous ammonia and 1,000 gallons of IOX. More significant, however, Tahikol had to man-rate the engine, i.e., make it safe enough for operation in a piloted airplane, capable of repeated use, and both throttleable and restartable in flight. This was not easy to achieve, particularly as its high-speed turbopump, a potential source of disaster, fed the engine propellants at a rate of 167 pounds per second. Eventually, the XLR-99 became a reliable power plant, with a rated operational life of about 1 hour, about 40 flights before requiring overhaul. Such reliability came at a price for a far longer than anticipated development period, compelling North American to complete the first 2 X-15s with older XLR-11 engines for their proving flights. The X-15 required a complex flight control system, a conventional fighter-like stick controlled an all-moving tail that furnished pitch and roll control, but was used only during approach and landing. During high G acceleration, climb, and reentry, the pilot relied on a side-stick controller. A reaction control system operating small hydrogen peroxide jet thrusters located in the nose and wings furnished pitch, roll, and yaw inputs at high altitudes, where conventional controls were ineffective. Eventually, the third X-15s flew with an adaptive flight control system that automatically compensated for changing dynamic pressure, blending the reactor control system with the conventional aerodynamic controls. Since the X-15 was technically a boost glider, once it exhausted its propellants, the pilot had to carefully manage his energy to ensure he could reach Rogers Dry Lake. To help him in doing this, the X-15 would always be flown so that it had excess energy at burnout, which the pilot could use as bleed-off using large pedal-like speed brakes installed in the side of a massive dorsal and ventral fins. Unlike earlier rocket-powered aircraft that flew near Edwards AFB, the X-15 demanded a special flight test corridor, dubbed the High Range, running roughly 480 miles from Wendover, Utah, southwest to Edwards. Crossing multiple mountain ranges in the stark southwestern desert, the High Range was itself a notable technical accomplishment, foreshadowing the manned spacecraft tracking network NASA established for Project Mercury several years later. NASA furnished 2 tracking stations at Ely and Beatty, Nevada, as well as at Edwards. Furthermore, unlike research airplanes, the X-15 required a complex flight simulator to train pilots and undertake mission planning and rehearsal. The simulator was updated using data required during X-15 flights, with pilots typically spending 40 to 50 hours in it before undertaking a 10 to a 12-minute flight. When the program commenced, it was hoped the X-15 might be flying by the end of 1957. Due to the complexity of its design and technical challenges involved, however, test flights did not begin until 1959. In the interim, NASA and the Air Force supported the X-15 development effort with extensive wind tunnel and free flight ballistic tunnel testing, evaluated reaction controls on ground simulator rigs and on modified research airplanes including the Bell X-1B and F-104, and undertook extensive simulation studies to prepare for the crucial challenges faced by a hypersonic rocket plane having, for its first time, the lowest lift-to-drag ratio ever flown on a piloted aircraft. In October 1957, Sputnik had seized the public imagination, and the national debate over American science and technology that followed, NACA had given way to the space-focused NASA. Now the X-15 took on greater urgency and visibility as a symbol of America's progression into space. Vice President Richard Nixon presided over its rollout at North American's Los Angeles facility on October 15, 1958. A year after the Soviet satellite ushered in the new space age. It was a remarkable-looking aircraft, burnished metallic black, with thin wings and horizontal tail surfaces, and, because of the directional stability requirements of high supersonic and hypersonic flight, large meat-cleaver dorsal and ventral vertical fins, the lower half of the ventral surface jettisonable during landing approach so that the X-15's landing skids could be a reasonable size. Although planners had originally thought the X-15 would use a modified Convair B-36 as a mothership, the retirement of the B-36 and the availability of the more powerful and capable B-52A led to its substitution for Convair's giant intercontinental bomber. Early tests with the X-15 proved far from encouraging. Piloted by North American test pilot Scott Crossfield, who had been so dedicated to the project that, as it began, he left NACA for North American, the first X-15, AF-56-6670, made its maiden captive flight on March 10, 1959, followed by its first glide flight on June 8th. During the landing approach, Crossfield encountered serious longitudinal control problems that pushed his piloting skills to the limit, necessitating adjustments to the boosted flight control system. The second X-15, AF-56-6671, made the type's first powered flight on September 17th. Propelled by two XLR-11 engines, it reached Mach 2.11 at 52,341 feet. He completed another powered flight into Mach 2.15 a month later, but then, on November 5th, disaster struck when an engine fire forced an emergency landing on Rosamond Dry Lake, during which 6,671 broke its back. While the second X-15 returned to North American for repairs and installation of its XLR-99, proving flights continued through 1960, with 6670 still equipped with its interim XLR-11s. The third X-15, AF-56-6672, was the first completed with the big Tahicle XLR-99. But during an Edwards ground test, the engine blew up, catapulting the rest of the airplane forward. Safe in its cockpit, Crossfield marveled at the X-15's strength and worried for the safety of crews trying to extricate him. The plane, like the second X-15, returned to North American for a rebuild. Not until November 15, 1960, 3 years late, would the X-15 fly with its XLR-99 engine, when Crossfield took 6671 to Mach 2.97, marking the end of its contractor flight test program. But now, the X-15 hits its stride. On March 7, 1961, Air Force Major Robert M. White became the first pilot to exceed Mach 4. He piloted the second X-15 across the hypersonic divide on June 23rd, attaining Mach 5.72. White completed a sonic trifecta by exceeding Mach 6 on November 9th, as previously mentioned. Nor was the boyish airman the X-15's only record setter. On August 22, 1963, NASA research pilot Joseph Walker attained 354,200 feet in the third X-15, taking it into space. Marring this was a serious landing accident on November 9, 1962, that virtually destroyed the second X-15 and seriously injured NASA pilots Jack McKay. When an engine failure necessitated a heavyweight emergency landing on Mud Lake, 6671's skid landing gear collapsed. Even this setback was turned to advantage, for NASA lengthened the X-15 and added provisions for 2 huge drop tanks and a dummy supersonic combustion ramjet engine installation on the shortened lower vertical fin. Eventually, on October 3, 1967, Major William J. Pete Knight reached Mach 6.7 flying this aircraft, designated the X-15A2. During the flight, unanticipated heating led to multiple structural failures, causing the Scramjet module to separate from the aircraft and damaging the fuel jettison system. Knight, a superlative airman, landed safely. Sadly, shortly after Knight's remarkable flight, the fastest by a piloted airplane in the 20th century, Air Force test pilot Major Michael Adams, was killed in the third X-15. On November 15, 1967, during a high-altitude flight, it entered a Mach 5 plus spin, and it broke well above Mach 4, during an inverted dive into the lower atmosphere. The accident stemmed from a fatal combustion of instrumentation and control systems failures, plus human factors. Less than a year later, on October 24, 1968, the X-15 completed its last flight, its 199th, flown by NASA pilot William Dana. NASA attempted a 200th flight on December 20th, but Edward was typically swathed in snow. Planners took it as an omen and simply retired the craft. The first X-15 went to the National Air and Space Museum, where it may be seen in the Milestones of Flight Gallery, and the second, the fastest airplane of the 20th century, to the National Museum of the U.S. Air Force. Altogether, 12 distinguished pilots, Scott Crossfield, Robert White, Forrest Peterston, Neil Armstrong, Joe Walker, Jack McKay, Milt Thompson, Robert Rushworth, Mike Adams, Bill Dana, Pete Knight, and Joe Engel had flown the X-15 to speeds and altitudes never previously achieved by winged vehicles. Its research program consisted of an aerodynamic and structural heating investigation phase from 1959 through 1963, and a follow-on program utilizing the X-15 to carry experiments into the upper atmosphere or to hypersonic speeds. Much of the applications program benefited from the contemporaneous Apollo effort, but it also helped sensor and missile detection efforts. X-15 flights produced more than 700 technical reports, establishing a database still considered essential today, as hypersonics advances into the second century of flight. The X-15 was by no means a perfect research vehicle. Under some circumstances, it had dangerous flight characteristics, and heavy impact loads sorely texted its landing skids. During reentry, in-flight reconnaissance effects could interact with its flight control system. Early on, researchers discovered gaps in panels that permitted the entry of hot hypersonic air into its structure, necessitating fixes. Cockpit outer window panels shattered from heat-distorted panel frame structural loads, forcing redesign, and its nose landing gear twice extended in flight due to thermal stress. There were several landing incidents and accidents, one major ground explosion, and, of course, the sad loss of the third X-15 with Mike Adams. But overall, as a product of the pre-computer design era, and without the benefit of modern tools such as computational fluid dynamics and computer-aided design and manufacturing, the X-15 constituted a remarkable achievement, and an astonishing productive research program bridging the age of flight and the age of space. Fittingly, two of its most distinguished pilots went on to greater fame in the U.S. space program. Neil Armstrong became the first man to walk on the moon, and Joe Engel became one of NASA's first space shuttle mission commanders. Today, Air Force and NASA researchers pursue Mach 6 hypersonic flight with the air-breathing Boeing Pratt & Whitney Rocketdyne X-51A WaveRider Scramjet research vehicle. Tellingly, its designation, X-51, was deliberately chosen and reserved to echo the X-15 and remind researchers of the remarkable aircraft that, a half a century ago, did so much to make hypersonic flight a reality.
Sir, if I can ask you the tough question first, if you could give us your name and the spelling of your name.
My name is Albert Scott Crossfield, Jr. ALBERTSCOTTCROSSFIELD JR.
With the period at the end.
Yeah.
Where were you born, sir?
I was born in Berkeley, California.
What was life like in Berkeley in those days?
I don't know. We left Berkeley when I was less than a year old. My father was a professor at King University of California, and a petroleum chemist that worked for the Union Oil Company there at Oleum. In fact, he helped build that refinery there.
Where did you move to?
We moved from there to Long Beach and then to Wilmington, California, which is the harbor of Los Angeles. And my father was material in building that big Union Oil refinery there on the hill in San Pedro, and he was superintendent of that refinery.
What was your childhood like?
What was it like? Well, I was a kid. No, I was raised mostly in Wilmington till I was about 14 years old. I was not well as a youngster. Had rheumatic fever very badly, which should have precluded all of my flight career, but I never let anybody know it. And 1935, when I was 14, we moved to the state of Washington. It was Depression days. My father was in the oil business, and that wasn't doing well, and he wanted to get back to the land and get away from the business world, which wasn't doing very well in the early 30s. So we moved up to a farm in the state of Washington, and he and I built that farm over the next few years and got it back on a profitable basis. And probably was a godsend for me in my physical condition, because I didn't have time, wasn't allowed to be sick. That was my father's nature. And I got to be a pretty strong farm kid and managed to get along pretty well after that physically.
You had your first ride in a plane when you were 6?
Yeah, I rode in an Alexander Eagle Rock with a guy named Carl Lenish, who was a chemist for the Union Oil Company and had been a World War I military pilot. And as collateral duties with the company, he used to fly the company airplanes. The Union Oil Company, I think, probably started the first business aviation fleet. And my father was a good friend of his. And he flew me, I believe, the first flight I ever had, he flew me from Monrovia Airport to Burbank, where we saw Pancho Barnes. And I've known her ever since, or known of her mostly. Of course, I was just a little kid. She didn't have much to do with little kids in those days. And she was typically Pancho Barnes. A heart as big as the world, goggles shoved back on her helmet, on her head, smoking black Mexican cigarillos, and murdering the Queen's English with 4-letter words in every sentence, and quite a gal.
So was that where the love of aviation came from, that first flight?
I think it was my generation. What was exciting, all through the 20s and 30s were airplanes. And we all built model airplanes from the time we could hold a stick. Free flight models. Learned an awful lot from the model airplane news and all of us getting together and competing. And it may have helped. Undoubtedly it helped. But I went to sleep on that first flight up in the front cockpit. So they tell me. I don't really remember if I did or not. But no, my generation was aviation-oriented, much as this generation's computer-oriented.
So when you were 12, you started taking flying lessons at 12?
At Wilmington Airport in California, it was right up where now the Figueroa Freeway goes through Wilmington, was an old slough, and a guy named Von McNulty was starving to death on that airport. And he needed a newspaper, so I delivered him a newspaper all month long, the Long Beach Press Telegram. and helped him clean up his airplanes from the mud on that slough. And my reward was about a half hour, an hour flight instruction every month. That's where I started.
What did it feel like to be flying a plane at the age of 12?
At 12 or any time you're flying, you don't take time for psychological analysis. I enjoyed it. I thought it was the way to go. That's about all I could say.
Now, where were you when you heard that Pearl Harbor had been bombed?
I was working for Boeing that Sunday morning. We were working overtime. I worked on the A-20 line at Boeing in Seattle. And the news came over. There weren't too many people in the plant on Sunday. And I heard that, and of course we didn't do much work that day. We listened to the radio and speculated. And I frankly thought this is going to be a biggie. And I have to get in it, and probably won't live through it. Generally, that had to be the attitude. You see, we're taking on two of the biggest navies and armies in the world. But I went to the University of Washington in 1940, and in 41, I quit that fall to go to Boeing to make enough money to go to school. I'd run out of money.
You thought that there was a good possibility that you would die in the war?
Well, that's a probability of anybody in a war, and I was determined I was going to fly in the war. I knew damn good and well I had a bigger job getting into the Air Corps and the Navy than I had flying. And I managed to work that through many devious channels, and went into the Air Force right after Pearl Harbor. And they sent me down to Willie Field, Arizona, and it was just a sea of young people. And we just got off the train, and they gave us a ticket home and said, "Don't call us, we'll call you." You know, they couldn't feed them, they had no clothes for them. Everybody joined. So I went back and got my job back at Boeing for a while, and decided if this war is going to be over for, I can go win it. And so I switched over and went over to the Navy, and they were glad to snatch up a potential Army recruit. And so I was in the Navy for the 4 years of World War II.
What did you do during the war, sir?
I was an instructor and fighter and gunnery instructor at Corpus Christi, Texas, most of the war, up for 32 months. And in 1944, I finally got orders to the fleet, and ended up after a few moves with Air Group 51, and we were staging for the invasion when the war was over.
Where were you when you heard about that the bomb had been dropped?
Pearl Harbor. The day the bomb had dropped, we were flying a lot of patrols over Pearl Harbor because the Navy was real goosey about what the Japanese might do. And I'll never forget that day, because as far as I could see were ships. Ships of the line, battleships, cruisers, destroyers, carriers, 200 carriers, I'd guess, loaded to the gunnels with airplanes, troop ships low in the water, supply ships. They're sitting up at 30,000 feet just putting in the time in case there was some kind of a raid on us. And I can remember just thinking, in less than a month, all of that's going to be on the bottom, because it was going to be a tough fight to get into Japan. They had 5 air groups assigned to my ship for the first week, not 5 pilots, 5 air groups, if she were still afloat. We were going to support the 2nd Marines going in right below Tokyo, and they were at double strength and had another double strength division right behind them, figuring they'd be pretty well wiped out the first day. And we knew that there was no way we were going to get back from that one. And our ship was pulling out the next day, actually, so I don't know how soon the invasion would have been. Got back to Pearl, and when I got back, something had happened. And we didn't know what. We didn't know if it was good or bad, but something had happened. The atmosphere just told you that. And then that night, actually we went back to Maui. We flew back to Maui that night. And that night the word came out they dropped this bomb, and that it'd probably signal the end of the war. Some celebration on that island. These people that have ventured, the Japanese were about to give up. They're absolutely wrong. They're trying to rewrite history, which is kind of what we were fighting. This was a religious war by then. It was an ethnic and religious war. They had 10,000 kamikazes waiting for us, and everything in the world to throw at us going in there. It would have been one heck of a landing to make that one, because we didn't have Britain 30 miles behind us with San Diego 3,000 miles away. You know, and that was going to be a very interesting. I think we would have won it, but it would have been a terrible price. Thank God for that bomb. Thank God for Tibbets.
When you heard that the bomb had been dropped, did everyone realize the war was over at that point, or did they?
No, but it was a big plus. And then when the second bomb was dropped, it pretty well concluded that the war was coming to an end fast. They couldn't take a beating like that, particularly after we saw the results. You know, the word got out pretty fast, and the pictures. And we had been pretty close to the intelligence on the war for quite a while, and the air groups that were going in. And everything was 180 degrees reversed. Going in, it was going to be a tough thing. And we were working, incidentally, for about almost 8 weeks with the 2nd Marines, using live ammunition, supporting them on several times a week. They'd make a landing on Maui, and we would work out how we were going to go into Japan. And it didn't look like it was doable, but we would have done it. So it was just really the mass of people we would have thrown at. So we knew the war was over. We were pretty sure it was coming to a close pretty fast that night. It was quite a celebration.
What was going on? The celebration? What type of celebration?
Well, everybody got drunk and disorderly. How do military men celebrate?
After World War II, you were back to school?
I went back to University of Washington, started to work at University of Washington wind tunnel, and stayed there until 49. I took most of my engineering over because I'd forgotten so much of it. And then Engine Charlie Wilson was Secretary of Defense at that time, I guess Secretary of War, huh? I've forgotten when they changed that. Defense. And he wasn't hiring anybody, and I could make more money working for the university, so I stayed and got our master's degree in aeronautical engineering, and then in 1950. In the meantime, I'd worked with the Navy to build the reserves up. Originally, they didn't have any money for a couple of years for pay, but we knew that we had to hold the capability together. I had a lot of fun then, too. I had the 13th Naval District Aerobatics team and Corsairs. That was a lot of fun.
At what point did you get to Edwards?
When I graduated, I went to Edwards in June of 1950. There wasn't much money in being an engineer in those days, and so it occurred to me that if I went back to flying, I could add something to it. I hadn't really planned on doing that. It was one of the options, but that, wasn't my main one. And I went to hitched a ride with the Navy down to Moffett Field, and I'd heard they had an opening down there, but I decided not to ask them if I could come down because they'd say, "Oh, I'll come down in a couple of weeks or make an appointment." It'd be too late, so I just went down and walked in their office. Surprisingly enough, they were expecting me. And my wife, who had never opened mail in her life of mine before that or since then, saw a letter that came from NACA and thought maybe that was important. So she opened it, and there was a request to negotiate for an interview with Edwards people at what was then the high-speed flight station. So being at Moffett Field, I got myself down to Edwards and beat everybody else there that letter had gotten to. And I was hired by Walt Williams as an aeronautical research pilot for the NACA.
Did you know much about the program before that?
Oh, yeah. Yeah, we've been following the X-1. In fact, I volunteered to fly the X-1 for nothing when Slick Goodland was trying to get all that big money. I thought that might be a pretty good step in the profession.
You were actually the first one to fly the X-1, weren't you?
No. Slick Goodland first flew the X-1, and then a number of Air Force pilots, including Chuck Yeager. He doesn't like Charlie. I call him Charlie because Pete Everest introduced me to him as Charlie one time, and I thought all his friends called him Charlie, so I started doing that. Got to be a habit, but I think I'm probably not a good enough friend to his to call him Charlie. No, he was the first to fly Mach 1 in the X-1, and that would have been in 1948. That's before I got there.
It says in one of your introductions that you are the only pilot who has ever worn out a pressure suit. Is that true?
I don't know. It could be. I wore a lot of pressure suits and helped develop our first full pressure suit, but that could be. I wore it a lot of times.
You logged a lot of miles, didn't you? A lot of hours.
Not a lot of hours. You know, I've got, I think, somewhere around 130, 140 rocket flights and only about 40 hours. They're not too long flights.
To somebody, for most of us, who will never be able to do that, describe what that's like.
It's a challenge. It's a lot of fun. It could be dangerous if you weren't up on the edge of your seat paying attention to business. And that's about all I can describe of it. We really wrote the book for almost everything we've done in aeronautics with the research airplanes in those days. And we never really had much in the way of information in the transonic area. Nobody did. And we gathered it all with those airplanes, with a variety of configurations and power plants and that sort of thing to see which way to go. And we used small rocket engines in those days. In fact, we did almost all the successful rocket work in spite of all of the publicity that the Germans brought the rockets over here. When they got over here, they all we know is what Goddard taught us. And before that crowd at Huntsville ever made one that worked, I had 50 rocket flights and several rocket airplanes at that time. And so we pioneered the rocket business. They're small, but it's a matter of caliber, not system. They were identical systems. And the X-1, of course, was first to Mach 1. The X-2 was built to go to Mach 5. The X-3 was to look at thin wing configurations. The X-4 was a tailless airplane. The X-5 was a variable sweep airplane. It was just looking at everything we could imagine. The XF-92 was a Delta. I flew all of those airplanes except the X-2 and the X-3. The D-5581 and 2 were Navy-funded airplanes in the same program. They just didn't put an X on them. They just left the manufacturer's number on them. And actually, the D-5581 was a jet-powered X-1 that would be able to sustain periods of time at high speeds. Not as high as the X-1, though. I don't believe it ever went supersonic. I think Gene May claimed it did, but I don't know if it really did or not. The D-5582 wrote the book for all of our swept-wing airplanes today. Really, it was the real workhorse to gain all of the information we needed for transonic swept wings. And almost everything on our airliners and our fighters today came out of that basic work.
Describe the atmosphere at that time at Edwards, what the people were like, what it was like, whether you guys knew you were making history.
It was so different from today, it's awful hard to describe it. It's like a small town, you knew everybody. We put more faith in our professional judgment than we did in computers and endorsements and agreements and all of that. Never once thought of insurance or risk. Well, we thought of risk, but we calculated that. We didn't calculate it. We thought it out pretty much, and it proved to be a good way to do it. And it was very disciplined in the way we did it, but not technically disciplined because we didn't know. And very often every flight for weeks would be into an area that we hadn't gone into. And all of it was on the envelopes of these airplanes that had unknown characteristics, but we solved a lot of problems. The problems with tailless swept-wing airplanes that killed Jeffrey de Havilland and made such a problem for the Navy. I've forgotten what's the one that Chance Vaught made, their tailless airplane. We found out why those airplanes, we didn't solve the problem, we found out why those airplanes were so given so many problems. Well, with the supersonic airplanes, they were all rockets then. We there at NACA, or I did, with Bill Bridgman from Douglas, figured out how to fly in the region's so-called supersonic yaw that was supposed to be lethal, that did end Yeager and Murray and Mel App. And we learned to handle that. Those things taught us how to get there next time around, like with the X-15, the X-2. But mainly it was to find out those characteristics an airplane had to have so it could be controlled by a man and, as part of the system. And handling qualities were the main things we were looking for. Pitch up was a characteristic of swept wings. It was very, it gets your attention. The airplane would pitch up low altitude where the air was dense, it'd pitch up to destruction. At higher altitudes where we did it, it would pitch up to stall. We found ways to relieve or inhibit that. And that's what that was all. It was all experimental, and really one good experiment is worth all the calculations in the world, because we're not smart enough to outguess Mother Nature without going out and try it.
Was it a very competitive place? You all competitive with one another?
Yes. I'm not supposed to say, oh no, we were all a team. That's a bunch of baloney. Fighter ops were down the runway from us. This was originally when I went there, a little 5,000-foot strip and some Butler and World War II buildings. And we got more done there in that atmosphere than we did when the place got real formal with a lot of permanent buildings. But they're all fighter pilots, and they're born competitive, and if they weren't, they sure were taught to be during the war. And so people say, how were you chosen to be a rocket pilot? I wasn't chosen, I chose myself. That's what I was going to do, and I won my spurs. So did other guys, a lot more. I mean, I wasn't alone in doing that. It was a strange business. Actually, the way it was run at the old NACA there would be a delight to run something like that today. People trusted one another. The engineers, and I'm an engineer, and I and the head of the station were talking about tomorrow's flight, and I was uncomfortable about something. He always said, you heard the pilot, and he gave me 24 hours to decide what to do about, or to go do it anyway, or not do it. But he always gave me that latitude. So it gave us an opportunity to think out what we were doing. And you never were pressured, even though probably I was the most pressured at that. I hated just sitting around waiting for, it was not a fast-moving business. Research never is, And in those days, we had no truck with publicity or that sort of thing. It was beneath us. We were technical people. We were research people. We didn't need all those flocks screwing around with us. But that thing was changing pretty fast about early 1950s. And we were approaching the McNamara era where everything had to be very carefully orchestrated and in a fishbowl. And so it was fun. And we then flew 11 research airplanes in the early 50s. with 70 people, all up, including the janitors, out of one hangar at the South Base at Edwards, and never been duplicated because we were on our own doing what we thought we could do and didn't have to clear it with anybody and weren't worried about making a mistake in front of the public. So that's been the biggest inhibition on progress that I think anything that's happened since World War II. And as an aside, that generation that came out of the Depression and World War II was very remarkable. And what we did with technology after the war, during the war, and after the war was really no precedent in history for it. But the bureaucracy that generation built, there's been no precedent for. We even made the Russians look like bikers. Still are. So, and that's really the big burden that everything is carrying, huh?
Did your background as an engineer give you kind of a leg up on most of the other pilots?
Yes and no. In the first place, it would be a criticism of the other pilots if I said it did, but that was the beginning of the era when almost all test pilots required to have an aeronautical or an engineering degree and that sort of thing. Things were changing then. Actually, Eddie Allen, who was an NACA pilot in the early 20s, was a legitimate doctor in his own right, and so was Jim Doolittle. And that really was where the precedent came from. After the war, we had a lot of goggles and flying scarf fighter pilots who were doggone good aviators and did most of the test flying, but really didn't wholly participate in the analysis and determination of what that was doing. During the 50s, that all changed. And at that time, the Air Force had a very strong inclination to want to be in on first flights and all of that. They soon found that that wasn't their business, huh? They were weapons system evaluators and not engineers. And so that came and went. And from then on, though, almost all Air Force and civilian test pilots were degreed engineers.
What makes a great test pilot?
I don't know what makes a beautiful woman, huh? I don't know. If you test pilots, I've seen them. They're tall and slim and short and fat, and they're just all kinds. I never did know what made a fighter pilot, and I trained hundreds of them. I never could anticipate by getting to know a student whether he was going to be good, bad, or indifferent. I never did know whether you had to push them or pull them or make them mad at you to make them do their best. I did know that the only thing I could do was to make them do their best. It's the best I could do for them. Well, test pilots, you know, it's got a lot of press and a lot of movies and a lot of stuff, but it's a good professional way to close the circle of engineering, you know, from concept all the way through the 7 steps to a finished product. Never before did we close it in engineering. We gave it to a pilot to see if it would work, and now he closed the circle. It's a dangerous business. If you claim that you never got scared, you're a liar and you shouldn't be a test pilot. You didn't have good sense. If you admitted you got scared, you probably shouldn't be a test pilot either, but except to yourself. And, it took an immense amount of concentration to not make those mistakes that very often could be fatal.
In the public's mind, I think test pilots are, excuse me, they're viewed as daredevils, but it's exactly the opposite, isn't it?
It became that way. Originally, right after the war, well, not necessarily all the time, because certainly the Wrights were good test pilots, the best in the world, weren't they? And they weren't daredevils, but they dared. And this is all the way up through the men who really carried aviation on its back when it had no precedent, no basis. And fact, we did much better before we had a history than we've done since we had a history. But out of World War II, of course, there were a lot of guys came out of the war still hyped up from the war, and a lot of them became test pilots. And some of the best pilots in both military services, that's the route they chose to take. They were inclined to be, I want to put it right, they weren't daredevils because they had good sense and they knew what they were doing. It is to be less introspective into what they were doing, and they wanted to fly. They loved to fly. That's probably one of the things that's a criteria for a test pilot. If he doesn't like to fly, he's got no business doing that kind of work. And then test pilots are all different too. Testing is a pretty broad profession. The work I was doing was so-called research, where we were finding out what the aerodynamics of different configurations of airplanes were. Test flying for a corporation was to see if our latest attempt to use all of those data and make a useful, applicable device were. That's a different thing. It's a demonstration of our engineering rather than a seeking of engineering parameters.
Now, you were the first pilot to, at least unofficially, go past Mach 3?
Unofficially, yeah. I knew Joe Walker was going to try it within a week or two, and so I had the opportunity, and I bumped that Mach meter up against Mach 3, and I didn't dare tell anybody, because that's very unprofessional. One, trying to steal another guy's plan, and two, doing what you didn't have on your flight plan. I'd fire a pilot that did that.
What was it like?
Nothing, just a number on a dial. I'm not even sure the number was good, because in those days we didn't have all that good of instruments. We should have, the instruments that were recording the stuff in the X-15, which is what I did it in, would have determined it. But what I got from the Mach meter in the cockpit probably was Mach 3. But I just did it so I could have that personal satisfaction. I didn't admit it for a long time.
Do you ever look back on those days and say, boy, I'm lucky to be alive right now. I did some crazy things, or things I didn't even know were crazy at the time?
I never dwelled on it in that regard. I knew the hazards of aviation. Of course, I lost an awful lot of friends in airplanes, because it's really all I've been involved in, particularly during the war. But aviation's not as dangerous as you'd like it. I was the engineering officer of a training squadron as a collateral duty in World War II down Corpus Christi. And in my tour in that squadron, we flew 550,000 hours. Now, that's a lot of hours. And we had 11 fatalities, instructors and students. When you think of that, pushing all those young people in through for the war, not letting up at all on them, that's pretty remarkable. For the research airplanes, we flew for 30 years, and we lost 5 pilots. And that's not bad. Now, that's not the high hours that we're talking about. But, and every one of those were dead before they left the ground, and that is, somebody made a mistake and going to do something they couldn't handle. And some of them were pretty close and lived through it. Charlie Yeager survived a couple of real close ones.
Tell me a little bit about the X-15.
Well, the X-15 was to be the natural follow-on to the X-2, which fell out of the picture pretty early, so it was a very unique kind of an airplane, and it did not have a good reputation amongst the people who had all the answers. Kelly Johnson said it would do nothing but prove the bravery of the pilot. Well, in the end, it turned out to be one of the most productive research vehicles we ever had, and probably paved a lot of ground going into space that we wouldn't have had information on, both with atmosphere, heating rates, aerodynamics, and all those things that it takes. The X-15 originally was planned to go 6,600 feet per second, fly 250,000 feet, and it did that. when we first proposed it, I decided that I was going to follow that airplane. I didn't want to leave the committee, but it was just such an opportunity that I made a deal with 2 or 3 of the manufacturers that I wanted to talk to them about working on the airplane during its whole development and manufacture as an engineer, and then take it into flight test. North American got it, and I got that opportunity. And I was 3 years in the design group on the X-15. I think I contributed to it. And then I took it into flight test and did the demonstration flights on it. And that was very interesting. The X-15 was like a bucking stallion, I'll tell you. It was going to kill me, or we were at a Mexican standoff for a while. But we finally broke it, and it turned out to be a good mount.
What are you most proud of in your career?
Just a good professional try. No particular thing. I'm proud of the X-15, but I can't be, because so many people had so much to do with it, who none of whom could have, or all of whom would have been missed terribly. And so just seeing an opportunity, that came out of the war, and for me, what I wanted to do, and taking advantage of that as much as I could. I'd like to go back and do some of it over again, but I don't have any particular single moment.
What would you like to go back and do over again?
Oh, professionally, I think maybe I could have hung in there a little bit better. I was inclined to stand on principle, and all that did was get me kicked off a program, so I couldn't do anything about what I was arguing about. That doesn't make very good sense in hindsight, does it? And a lot of people do that, I got fired 3 times, and I'm pretty proud of twice. So.
Was mostly the bureaucracy that you were fighting against?
Not the bureaucracy. I don't know how to discuss those things without being negative, And it serves no purpose. I got fired off of the Apollo because I stood up against NASA. And you didn't stand up against NASA, particularly if you were a customer who was getting $2 billion a year out of them. And so NASA recommended North American that I be removed from the job, and I was on the Apollo. Frankly, though, I think that what we were fighting for, we won, and we got to the moon, and that was to discipline these things without any yielding to those disciplines that would guarantee that Armstrong would get back. My first battle with NASA was 3 years before the fire. We knew it was going to happen, and we fought like hell to find another way to do that ground test where we were going to have that very high total pressure of pure oxygen in that cockpit. But no, sir, NASA was going to do it their way, and I was told to shut up or get off the program. So I shut up. I regret that. And it wasn't that we were so smart, but we could demonstrate that explosion was almost inevitable. And that wasn't because we were so smart, because there had already been 2 men killed in identical circumstances. One at the School of Aviation Medicine, San Antonio, one at Wright Field. They kept that pretty quiet over the years. NASA knew that. But we had demonstrated at that time, I owned all the quality control, reliability engineering, and systems test on Apollo. And we were doing an incredible job. In 3 years, we went from 3,500 to 35,000, and we're testing hardware that was going to go to the moon. And those were long, hard days. But NASA did not like to be disagreed with. And I wouldn't criticize it, but Jim Webb blamed the company for that fire. And the company fought him tooth and nail against doing that. Both the aeromedical people and those of us in engineering. I did because I didn't know how we were going to test this thing at sea level. In space, 100% oxygen atmosphere is quite safe. It's only 5 psi absolute. But on the ground, it's 5 plus 15 atmospheric. 20 pounds absolute, and it's a thermite bomb. So it's those kinds of things that I stood up for that got me in trouble professionally, and so finally I just had to go to the airlines and work for them.
In terms of NASA, do you think there was too much pressure to get to the moon by the end of the 60s?
No. It was doable, and we did it. And a lot of things came up, and a lot of changes were made. It was hard to do, no question about it. No, that program was a killer, but it shows what we can do if we get a national commitment. Sometimes you wonder if we can't afford to assassinate a few more presidents so we can get national commitments, you know, which is not a very nice way to look at it, but that's what made it so that we all work together. And when this country decides to do something and they all work together, nothing's impossible. Nothing. I don't think anything is. It would be very difficult to go back to the moon right now because it'd be a political battle for money over everything, you know. But at those times when Jack died, well, that was his dream, and nobody dared vote against it, which is kind of good. It caught us back from our embarrassment of the Russians whipping our tail in space the way they were, with airplanes and space. You know, they were doing an incredibly good job. At first with supersonic transport, they beat us with a Mach 3 fighter. First in space, first with an animal in space, first with a man in space, and they've had that laboratory up there in space for 20 years. So all of us bragging. Well, the going to the moon kind of tempers a lot of that. We had a bad habit all those days of being a little bit long-nosed about Russian engineering, how it was crude and all of that. I beg your pardon, they are brilliant engineers, and they proved it over and over again. When they first opened up their Shanghai laboratory in 1993, I was over there, just happened to be there and happened to go. And I'm a wind tunnel aerodynamicist by training, and really originally a profession. They had wind tunnels that NASA would give their right arm to have, and they ran them on 1/10 of the budget that NASA runs them on. They didn't have all of the flack and the publicity and the show that went with it. They had concrete block walls with awful good tools. And they had some wind tunnels that were unbelievable, still are, and nothing matches in the United States today. And they would have been tough in a technological war. Well, they were tough, huh?
Anything that I've left out that you think is important?
I don't know. What's important is that I wish we could get out of this moratorium where we're living on World War II, how good we were, memorabilia, museums, legends of flight, all the things you guys are doing, and start put that kind of money, time, and effort in the future. And then we would take another explosive growth. It's going to happen, but we're not going to, the old guys aren't going to like the way the young people do it. But they're going to do it. The computers were that kind of thing, gave us tools. The bureaucracy made us think that the computers are smarter than we were, but we'll get over that too. But if you stop and think, all of this celebrating that we do about how good we are, if we could just put that kind of money and effort in the future. But the last try I had, and it took me almost 20 years to get it off the ground and go on, was the National Aerospace plane. We almost got over the hump, but we couldn't quite do it. And I got that canceled myself because I couldn't do to the taxpayer what they were doing. You know, it needed a leader, it needed a dedication, because when you do something that hard, it's like a war. You know, the leaders surface, but we just never got far enough into it that it would work. You know, the Kelly Johnsons and the Harrison Storms and those kind of guys. And they would have surfaced, but we couldn't go so long. They were already spent $3 billion. They hadn't drawn a center line, and yet you knew it was doable. I could make it doable on my home computer. But for some reason or other, everybody wanted to make a tremendous effort out of it. Much like when we started to talk about going to the moon, everybody said we couldn't. In fact, it wasn't until Kennedy died that it really got to be a serious effort. You know, and they just said, why don't we? So if anything that we're leaving out right now, we have done nothing really in space and aeronautics in the last 30, 40 years. The space station is a godsend. I wish it were all ours. It gives us the opportunity to make sure World War III never occurs, because we can look at the Earth pretty thoroughly and know what everybody's doing, and if we don't play Chamberlain, we'll stop them. We'll have to, because the next one's going to be a mean one. Well, they're all mean. But I work a lot with aerospace education, and we were talking a little bit earlier here with children and all that, but we're not going to push them into aviation and space. They're going to find their own way to do it. In fact, I think if we objected, they would move faster than if we tried to push them into it. That's the nature of young people, isn't it?
Magic that was there for a kid nowadays for aviation that there was when you were
No, no way. The Dayton kid isn't sitting on a fence dreaming anymore. And you know, we could fix that. I mean, there are a lot of ways if we just had the balls to do it. But today we count the beans and we get insurance, we don't take risks, we don't do this. And if a youngster wants to learn to fly today, what does he learn to fly? In a 152. Now, what bright up-and-coming young man wants to fly in a 152? But we have little jet engines today that, I want one of those, huh? And we could make a cheap trainer below $100,000, the cost of a sports car. And, but the risk, the cost, you know, that's the thing. The risk, nobody is willing to take a professional or a monetary risk this day and age. And the history of aviation are people going broke because their heart, you know, led way out in front. If you go to the Air and Space Museum, just stand in that foyer, look at all the heart that's in there. And not much of that costs much money. I can give an example, and that is that the research airplane program was 30 years up through the X-15, was about 30 variations of about 13 or 14 basic configurations. The whole cost of all that hardware and the operations over that 30 years was less than $500 million. $500 million, less than $500 million. You couldn't bid on one of those today. All of the reports that came out of the X-15 might be that thick. Your bid today would be that thick to make an X-15. And that's what was beginning to happen to the aerospace plane. It was doable. You could prove analytically that while there are a lot of things we had to learn, just like with the X-15 and the Apollo and everything else, that we could do it. But you have to do it with a lot of heart in it. And we've changed quite a bit. It used to be that a general would say, hey, do that, and he'd do it. But today he has to ask his colonels to study it, and then he has to follow their recommendation. And that's no way to run a ball game, I don't think. We could do an awful lot in aviation right now if we just made up our mind and go do it. And here I'm sitting here talking about it. Probably I should be doing it too. Well, the National Aerospace Plan was, we put out the first contract in 1986. And it was to be an effort to make an orbital turnaround vehicle that would go to space as an air breather. About 78% of the load lifted off of the Cape Canaveral on the space shuttle is oxygen. And it's to be had for free in the atmosphere. You know, every engine we have, except rockets, uses Earth's atmosphere to breathe. If we could do that, we could reduce the cost of going to space by maybe 2 orders of magnitude. Instead of $1,400 or $140, maybe $14 a pound. And it was a dream of a lot of us to now sophisticate all we learned through the brutishness of rocket technology, which is the only way we could do it. So we had a scheme for an air-breathing airplane that would take off from a runway, fly to orbit, and you can as an air breather. People say, oh, there's no air up there, but there are ways to do this. even if we did have to use rockets, and I would have accepted that, the last 3 or 4 Mach numbers, that's okay too, and return. And that would be kind of make the space station and the space shuttle really be meaningful, so we'd have some alacrity and flexibility and turnaround capability to go into space. And really, NASA was interested in Mars, and other people were talking about going to the moon, and I kind of think our problems here on Earth to solve these problems first. Cislunar space is where we're going to really get the advantage of these new technology. We've already got a tremendous advantage from it. Well, the aerospace plane was supposed to do that, and one of the derivatives was a Mach 5 transport. What Reagan called, or used our name, the Orient Express. I don't remember that. It would take aerospace plane technology to do the Orient Express, and it was very attractive in that you could fly from New York to Beijing in under 2 hours. And actually it turned out to be very good economically because, you know, time and speed is really where the economics come into this thing. But that didn't get very far. It did a lot of good, though, because my scheme was that we ought to be a nation against the world, much as Russia was, rather than a company against the world. So why not muster an alliance of all of our major airframe manufacturers to build a national aerospace plane? Then we get the benefit of all of the talent and input in the country, with a tremendous financial base to make it possible. We did that with materials. The phase 1 was just to look at all of the materials. And all of the engineering people from the 5 major manufacturers got together, and we had quantum leaps in our understanding of materials. High solidification ratio metals, you know, some of these glass metals that we had, controlling the structure, the crystal structure of metals and all of that, which just started a whole new world of materials. Carbon fibers are one of those things, and look at what we're getting out of carbon fiber material today, compound materials. And that worked pretty well, and everybody got together and shared it. And in that scheme, no company was barred from doing what they wanted, but each one of them had a main aim to take care of, you know, whether it be metals, organic materials, so whatever it was. But when we tried to do the aerospace plane, we had the 5 industries got together, and it was led by North American, which would have been a good leader, but they didn't put an engineer in charge. They put a Harvard MBA in charge. That was, I shouldn't be that critical, but nevertheless, the companies got to arguing about, well, you got the last engineering decision, let's vote. I want the next one. Well, you don't do that. And that was this bureaucracy working. And actually, they spent an awful lot of money and weren't getting anywhere. And so I talked to the congressman I was working with on this thing at the time. I was a technical advisor at Congress at that time. Told him, hey, let's cancel this. We can't do this to the taxpayer, you know. $3 billion before you get started, you know, and it would have been as expensive maybe as Apollo. But the results would have been well worthwhile. We would have shrunk the Earth down to size. We would have had a lot of commerce in space, not just one space station that we try to get money out of Russia to help us build and that sort of thing. But everyone had their own axe to grind rather than, it takes a leader, a real leader to lead a thing like that, and he didn't surface. That's really what.
Are we the same country? Do we have the same national character and national spirit that won World War II that could do the test pilot program, or has it all been lost?
Yeah. It's always been difficult to motivate this country. This goes from the Revolutionary War through the Civil War, the Spanish-American War. We've always been, you know, we can get together again to do anything. And we've had an awful lot of large immigration here since, say, Cuba and all of that. We've got, again, the best of the world in that, we're ready to do anything, and we can. That was a mistake that Hitler kind of seemed to think that we were decadent, you know, and we weren't going to be able to stand up to him. Well, he got his arse whipped. And we can do that again if necessary, and we're in a position to do it. Yes, we are the same country, though they're an awful... Nothing's perfect, I guess. This country's not perfect. It was constructed so that it's virtually indestructible as a system. And that's because, incidentally, 3 engineers designed the country, Washington, Jefferson, and Franklin. And they did. They used the engineering method. I could just lay out how we build our country to the engineering method. So when one part gets a little weak, the other parts can carry it. But it had its problems. Certainly there was not a union in the 1860s, huh? And there's still not a union. But when we go to war, we go to war. And we'll win it. I wish we could go to war with the technology that's there for us to do, because, you know, and use this computer here. These computers